In this video, the Fibonacci search method is explained. The Fibonacci search method is a 1D optimization method for finding the minimum of a unimodal function on a closed interval, without using derivatives. The core idea is that instead of splitting the interval in half, like bisection, it splits it using Fibonacci ratios. This guarantees the smallest possible final uncertainty for a fixed number of function evaluations. Phase 1, Initialization. We start by defining the following parameters: initial uncertainty interval, required accuracy, distinguishability constant, and the number of iterations. Once the number of iterations is determined, the initial test points are computed. Phase 2, Main loop. At each iteration, the objective function is evaluated at 2 points. The two objective functions are compared, and based on this comparison the minimum interval is determined. Phase 3, Final step. The calculations for the final step is different from the other steps, and it is defined here. At this point, the algorithm reaches the final stage. The remaining uncertainty interval is very small, and the standard Fibonacci ratios can no longer generate two distinct interior test points. Therefore, a small positive constant is introduced and the last test points are placed as follows, and the midpoint of the final interval is taken as a numerical estimate of the optimum. We now apply the method to the following optimization problem. The required accuracy is 0.2, the length of the initial interval is 8. We do the initialization calculations and obtain the objective functions for the first iteration. In the second iteration, by comparing the objective functions, we realize that case 2 applies here. So the calculations for new points and new objective functions are done based on case 2. For the third iteration, by comparing the objective functions, we realize that case 2 applies again. So as you can see, the calculations for new points and new objective functions are done based on case 2. At the fourth iteration, case 1 applies. So the calculations for new points and new objective functions are done based on case 1. At iteration 5, the comparison of the previous objective functions shows that case 2 applies here. So the calculations for new points and new objective functions are done based on case 2. At the sixth iteration, comparing the previous objective function values indicates that case 1 is applicable. Therefore, the new points and their corresponding objective function values are computed according to case 1. At iteration 7, the evaluation of the previous objective function values shows that case 1 is applied. Therefore, the new points and their corresponding objective function values are determined using case 1. At the eighth iteration, analysis of the previous objective function values indicates that case 2 applies. Consequently, the new points and their corresponding objective function values are computed based on case 2. At this point, the algorithm has reached its final iteration. The uncertainty interval has already been reduced as much as possible using Fibonacci ratios, so no further interior points can be generated in the usual way. Based on this comparison, the final uncertainty interval is selected. Next, the length of this final interval is checked against the required accuracy. Since the interval is now shorter than the prescribed tolerance, the stopping condition is satisfied and the algorithm terminates successfully. It is important to note that the Fibonacci search does not aim to compute an exact minimizer. Instead, it guarantees that the true optimal solution lies somewhere within the final uncertainty interval. A practical estimate of the solution is therefore obtained by taking the midpoint of this interval, which serves as a reliable approximation of the true minimum.